All right, this is class 13 and example 2. We're going to do a slider crank, and this is again an example from my draft book, the Engineering Dynamics Course Companion. For the slider crank, BC rotates at 8 radians per second clockwise, and theta is equal to 40. The dimensions are 500 crank, connecting rod, LAB is 500 millimeters, LBC is 300 millimeters, that's right here, and LBD, this little extension on the end, is 150, and we want to determine the velocity of point D, right up here. So I'm going to go ahead and, well, first off, I'll find this missing angle right here. We almost always start with some type of position analysis. And then we'll figure out what the velocity of B is going to be, which is actually the velocity of B with respect to C. And that's the value of it is just omega of BC right here times the length. And so that's going to be 2.4 meters per second. It's important to look at that, what that angle is going to be. If you're doing a problem and the angles are close to 45, it might be better to exaggerate a little bit more or a little bit less of the angle so that you could try to figure out which angles are going to match with each other. Or you could just memorize it, I guess. Or work out the different geometry. So in order to find, one of the first tasks almost always in any of these problems is to figure out what the angular velocity is going to be of the connecting rod, or of the piece that's connected. So here's the 3-diagram method. And we know what the velocity of B is, and we know the velocity of A is either to the left or the right, but it has to be along this line. So we write out the, well, I didn't write out the equation, but I should have. Let's see, somewhere in here, I should have written out, yeah, so I left it out of here, right? So I should have written somewhere in here that the velocity of A was equal to the velocity of B plus the velocity of A with respect to B, right? So, and that's looking at that point right there, and using B as the reference, right? So in the y direction, that's the easiest one to use first. We can see that there's no, it's going to be equal to 0, right? And the VB here that we're placing right there is going to be the cosine of theta times VB. And VB is something that we know. Because VB is something that we know, we're able to figure out what omega ABD is going to be. And by the way, that should have been a negative right in there. So what we find is as expected. Oh, and by the way, when doing this, we had to assume a direction, or we could have thought our way through it, right? So similar to what I had mentioned in a previous example coming up here, if you can use the 3-diagram method to think your way through what direction this has to rotate in order to make this true. VB is already going downwards. But there is no y component to VA. Therefore, this has to rotate clockwise about B in order for there to be a vertical component that would counteract the vertical component of VB. So that's what gives us this ability to find out what omega is, because this has no. Now, if that was not the case, right, if we didn't have one, we could do a couple other different tricks, but probably what would happen is we would have two equations, one in the y direction, one in the x direction, and then two unknowns. And one of those unknowns would be like the magnitude of VA, and the other would probably be omega. But so we'd have two equations and two unknowns, we'd be able to solve it. So now we go to the velocity at point D. And so I draw the 3 diagrams, a three diagram problem here, and I keep the velocities, just assume them positive as components right here. So this is the equation that I'm solving here. I'm solving for D using B as the reference. So again, I'm pinning it about here. And I already know the direction from that previous point. I know what the omega is going to be. So I'm able, let's see right here, to write out the velocity of D in the x direction is going to be, in this case, it's going to be the sine, right? So it's this component opposite VB times it, and it's positive. You notice it's going to the right. VD with respect to B is definitely going to be negative right here because it's going to be, that's going to be the x component, and it's going to be the sine of beta as part of that. So we're able to write what this has out, and we're able to get a value for it. Same thing for the y direction, but now it's going to be negative because obviously this is going downwards, that component, and then this is also going downwards, so they're both negative, and we use that omega right there, and we're able to find that. So we know that the velocity of D is going to be upwards, it turns out. All right, so it's going to be upwards and to the left, right? So wait a minute, I think I might, no, excuse me. It's going to be to the right and downwards, right? Because, sorry, this is x is positive, y is negative, so we're going to have the quadrant that's downwards, and we're able to figure out the magnitude. If we're going to do the instantaneous center of rotation method here, we already found that 22.6 degrees for the beta right here. Right, so we're able to find, and you know, it's easier to understand if you were to see this done, find the ICR from the original problem here. So let's go back to this figure, not here, not this one, it's a previous problem. Go back to here and take a look. We know that the velocity of B goes along this line, so the perpendicular line is like right up in here, and we know the velocity here is going to be across here, so the perpendicular line is right up here. So here's the location of the ICR. So that's the thought process that helps us get there. But you might also recall another diagram that we showed earlier in the section on the ICR showed us that situation there, where we had that ICR be the line being drawn through the point, and then the line being drawn as an extension through that arm to find that ICR. And so I'm gonna go through the rest of this. Sorry, I say sorry. You're not mad at me, right? Yeah, we're totally okay. All right, so. We get back up to here where we start to get to geometry. And so here's the way that I broke it out here. I found these like intermediate points into here. And I was able from this right here to figure out what the RA with respect to ICR was going to be. All right, so what I did by breaking it down, I found I found the segment LAE, right? I found this guy right here from this, right? So I got this dimension part of it right here, and then I was able to find LBE right here. I was able to find this dimension right in here from the cosine, and then I was able to find DF. Let's see where DF is going to be. I was able to find this dimension right there by finding this, using that side right here times the cosine. So I was able to find that. And then I was also able to find A to F. So that's going to be this dimension right up to here. I was able to find what A with respect to ICR is going to be by taking the tangent of, I say theta right here. Let me double check there. I believe, what am I calling theta? That's an interesting thing. I got to be careful right here. where the hell is theta? Oh, theta is this angle right here. Huh. Did I find that one right here? Let me see if that's true. On LAE, so I got LAE and BE. Where the hell is BE? Let me find BE. All right, so I got LAE and BE. Okay. I'm not certain I believe that to be true. All right, so that's going to be, and then I have the tangent of 40 degrees. Let's see, where's 40 degrees coming from? Did I get that from some other place? Oh, that's going to be this guy right here. Okay, so I know that's theta, and oh, and that's theta, and that's theta. Okay, all right, so that's how I got it. I'm sorry, sometimes I get myself mixed up as I'm walking through the thing. So let me go back and try to explain this. So I'm going to put another color in there as my reset. Right? I have theta as that angle that was given, and I know that's theta right there, so I know that's theta right here, so I know that this one has to be true right there, right? Because we know that that has to be perpendicular. That's fine. So what I'm trying to find right here, this distance that I'm trying to find, is going to be my BE, something I found up above right here, and the tangent. So this is the run, so that this is the rise. Yep, that's it right there. So that's what that is. That BE times the tangent of theta is going to be this line right here. And then AE is something that I already calculated up above right here. So then I know that dimension. And then if I want to get B with respect to ICR right here, I can use this is going to be, yes, okay, so I have, let me get rid of some of these so I can diagram them better. So I want to get this guy right here. What I can do is I could take LA and the cosine of theta, LA times the cosine of theta, this guy right here, and times this. That's going to be this dimension right here. So that's going to be BE. So I probably could have used that guy right there. I probably could have already used, I didn't have to call it LAB right here. I could have called this guy right here my LBE. And divided by the cosine of theta, and that would have given us this length right there, because that's the hypotenuse of this triangle. I'm telling you, sometimes the ICR is not the most convenient way to do things, because you have to play around with a little bit of geometry. And then lastly, I'm able to find the hypotenuse of this triangle right here to be able to find RD with respect to ICR, and I don't know where that R went right there. And that ends up landing us with the 6.6841. Oh, and you notice, yeah. So that this is the leg right here that's being represented by this right here, that we're having this guy right here that we found before, and we're subtracting out the A to F that we found up here, right here, and we're able to find that. There's probably easier ways to go about this, but this is the way that I did it. And then I'm also able to find this angle right here, noting that that angle is going to be the same as this angle. So with that information, I'm able to find omega, because I have velocity of B, right? I know what that is. and I know what that distance, I just found it, so I can get the angular velocity. And then I can find the velocity of A, although I don't think I was asked that, by multiplying that angular velocity. And we get the same thing as we got in the 3-diagram method. Now I can find the velocity of D, which was the point of the whole thing. And so that's going to be the angular velocity times that this RD with respect to ICR, and I'm able to find, and that's the same answer that we got previously. And then I'm able to find, well, the correct one with respect to horizontal. So this is the angle that we found on the previous page with respect to vertical, but it's actually this one that we want to try to find. And we're able to find what the answer is, which is the same as the previous example, which was numbered something else. So yeah, so taking a look at the results down here, we had 2.73 and 61.7 degrees, and here we get the same thing. And then I'll do one more example. So this is the end of this one.